be bigger than 2. So we've managed to do lots of things with polynomials of degree 2, right? If you need to solve a polynomial equation, you can do it. If you need to solve a polynomial inequality, you can do it. If you need to optimize a polynomial, you can do that. You can graph them. We've done some model building, what things are modeled by degree 2 polynomial things. One assumes that degree 2 polynomials don't do everything now. So you need to deal with other functions than just those. And that's what we're going to start in on today. And here's an example of where a polynomial of degree greater than 2 appears just in the wild. Suppose you have a 3x2 sheet of cardboard. You would like to do a thing where you like cut a wedge out of each corner and fold things up to make a box. So I guess the bad picture is, all right, so there's like a 3x2 sheet of cardboard. You're going to make a little cut at each corner, and then you're going to fold along these red dotted lines. You do that, you wind up building a box. Maybe drawing a picture is useful. There's the base of the box. I don't think I can draw any better a picture of a box than that. What do you think? Could we come up with a model that says what the volume of that box is for any given x? Yeah, what's the formula for the volume of the box? Yeah, base times the area, just the product of the dimensions. So let's just compute the various dimensions. So I guess this, like x that we cut out, we fold that up, that becomes the height. So this box has a height of x. This side, I guess, becomes that front side, the width. So what's the width of this box? 3 minus 2x? Oh, let me pause. So how many people who came in not 5 minutes early and so didn't get one of these? Okay. Thank you. Yeah. So, what about the other dimension? Yeah, great. You have that original length of 2. You cut out 2 of these x-sized corners. So this length is 2 minus 2x. That length is 2 minus 2x. So what is the volume of this box in terms of the size of each cut? So by looking at that picture, what's the volume of that box? It's the product of the 3, right? X times 2 minus 2x times 3 minus 2x. And this is obviously like a made-up example. I don't care that much about it, but you could imagine maybe you would want to construct this box in a way that maximizes volume. That seems like a reasonable thing to want to do. We don't have a good technique right now for how to maximize a degree 3 polynomial. And in fact, we won't ever have, in this class, a good technique to maximize all the no's. A good technique appears in calculus in the form of finding things called critical points. But, do you think we could graph that function? And we could just like eyeball what the maximum value is if we have a graph, right? So let's do that. X times 2 minus 2x times 3 minus 2x. So I guess that makes sense. If we don't do any cutting, then there's no volume. It's a sheet of cardboard. If we cut a total of 1 as the size of each cut, then we've just cut away a whole edge of the box. So there's nothing left, so beyond 2, the problem doesn't even make sense. So there's the domain 0 to 1. So what does it look like the maximum height, maximum volume is? Well, it's unfair, right? I'm the one who has the computer. It's like about there, I guess. So it looks like this. Leave that up. It sure looks like the maximum volume is around 1.06, and it corresponds to a choice of x equal to 0.39. Are there any units specified in this problem? Okay, so I can't give units because none were specified. Does that feel reasonable as a place where you might just encounter high-degree polynomials? Yeah. So now, let's wax a little bit more technical. Let's just talk about what do I mean by a polynomial. And I don't know, like we've said the word a few times, what do you think a polynomial means? So I guess informally it should be like a sum of a bunch of powers of x with a number next to it. So informally, what is a polynomial? A sum of multiples of powers of x. Fair enough. And when we can talk about the degree of a polynomial, that's just like, what's the biggest power of x that you see? So let's start by just writing some things down. So I'll start with degree 1, because degree 0 is kind of weird. A degree 1 polynomial is a linear function. It's something that looks like ax plus b. It's called a degree 1 polynomial because the biggest power of x I see is 1. So I guess a degree 0 polynomial, that's degree 1, then a degree 0 polynomial would just be something like that. Something that's constant. So a degree 0 polynomial is just a constant. So I guess maybe a is a silly thing to say, but it's just a number. 5 is a degree 0 polynomial. A degree 2 polynomial is a quadratic function. Where a, b, and c are just some numbers. A degree 3 polynomial is the same, but you go up to degree 3. And so on. Like, you get the pattern here. And maybe you can imagine that by the time I make it to a degree 26 polynomial, I will have run out of letters. In fact, before that, because x is already spoken for. So if you want to write down a degree d polynomial, we kind of know what the idea should be. It's a bunch of coefficients times powers of x, the biggest power is d. So that's what I'm about to write down. And I can't just use letters a, b, c, d, so maybe I'll write down something like this. It'll be some coefficient a sub d times x to the power d plus a sub d minus 1, x to the power d minus 1 plus, and I don't know how big d is, so I don't know, like I can't just keep writing terms, I won't know when to stop. So I'll just encode something with a dot, dot, dot. a1 times x plus a0. That seem believable? We're here, a1, a2, a0, a1, a2, dot, 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 dot. On through ad are constants. They're just numbers. That seem pretty okay? So I'm going to introduce a new bit of notation that I won't use very often. But if you have some formal sum like that, where there's like some dot, 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 and you have to like do it a few times, you probably don't want to write that more times than you absolutely must. So as a consequence, mathematicians come up with the following notation. So a mathematician would write that as a sum indicated by the Greek letter sigma, which is just used because it starts with an S sound, and so does the word sum, of things that look like ai x to the power I. So it's the sum, and it's a sum of things that look like that. And then I should tell you what types of i's you can see in that sum. It's the sum where I starts at 0 and goes all the way up to d. I won't use that notation much, but it's nice to know that there is a nice compact notation. And maybe another like sales pitch to calculus is one of the things that happens in second semester calculus is you start thinking about infinite sums and what those can mean. But then you definitely can't like write down all the terms, so you have to use some notation like that. So I haven't done much, and I won't do much today. But any questions so far? Cool. So I just want to start studying these polynomials, see what things you can do and how they do and don't behave like degree 2 polynomials. So let's ratchet up the degree just by one and just study degree 3 polynomials and see that their behavior is much more complicated. Oh no, I'm skipping something. We will do that. Classify the following as polynomials or not polynomials. Is 5 a polynomial? Vote for yes. Anyone for no? Those who said yes, what is its degree? 0. Right? A constant function is a degree 0 polynomial. It's silly to think of it as a polynomial. You should just think of it as a constant, but it is a polynomial. 1 divided by x, polynomial or not polynomial? Is it a polynomial? Is it not a polynomial? So anyone who said yes, what degree would you want that to have?
-1.
Cool. So I'm going to write not a polynomial. It is something that's like a polynomial, though. It's something that's division by a polynomial. This is something that we'll walk on soon. We'll think about things like that. This is called a rational function. So just in the technicality of what a polynomial means, you're only allowed to see positive powers of x. You're not allowed to see x inverses. That next one, that is a sum of multiples of powers of x. Is that third one a polynomial? Yeah, absolutely. It's just like, it's what a polynomial is. What's its degree? 5. Awesome. I guess we said this, but. All right. X plus 1 over x minus 1. Polynomial or not polynomial? Polynomial? Not polynomial. Good. Yeah, it's a rational function, something that we'll introduce in a little bit. A ratio of polynomials isn't a polynomial. It's probably not a polynomial. X plus 3 times x plus 2 times x plus 1. Polynomial? Non-polynomial. Cool. Those of you who said yes, what is its degree? 3. I guess the way you could see that is, imagine you FOILed it out. Don't actually do it, but imagine you FOILed it out. At the end of the day, would you see a bunch of multiples of powers of x? That's what a polynomial is. And the biggest power of x you would see, I guess, is 3. Gesundheit. 2 to the x. Is that a polynomial? Anyone for yes? Anyone for no? So that is not a polynomial. It's a different flavor of function, something that's called an exponential. So, I guess the point there is x can appear in a base of an exponent, but not in the exponent itself. Right? You're allowed x squared, but you're not allowed 2 to the x in a polynomial. Groovy. So, now that we have some classification, by the way, all of those things that aren't polynomials are things that we will study in the not too distant future. But let's focus on some degree 3 polynomials. Let's focus on those 4 degree 3 polynomials. Let's start by looking at their graphs, a graph of each of them. And we'll talk about some properties of them. So, stick with Desmos. I'm going to pull up graphs of those 3 polynomials. X cubed, x times 2x squared plus 1, 3x times x minus 1 times x plus 1, x times x minus 1 squared. All right, so I've got them all pulled up, but I think I want to look at them just one at a time. So there's the first of them. Its graph, well, you know what this graph looked like already, right? This is also a power function. So by looking at that graph, let's count some things. How many x-intercepts does this have? Just the one. How many turning points does it have? How many places are there where it goes from increasing to decreasing or decreasing to increasing? Does it have any? Yeah, so maybe you would want to say 0. It certainly is what in calculus you would call a turning point. But before 0, is it increasing or decreasing? Increasing. After 0, is it increasing or decreasing? Still increasing. So it's not actually a turning point. It looks like it kind of wants to be a turning point, but it's not quite a turning point. So it's got one root, no turning points. Second function. How many roots does it have? Well, okay, I should copy it down first. Still just the one. How many turning points? So by that measure, the green and the blue kind of have similar behavior, but what's something different about them? Yeah.
The second one is like flatter.
Yeah. Is this one the second one?
No, the green one is like flatter. Or like more straight.
Okay, yeah, I looked at one side. Yeah, so it looks at 0 like it's going through like a line. It's not slowing down and stopping. Nice. This third one, how many intercepts? X-intercepts? 3. How many turning points? So that's a different behavior from the previous ones. And this final one, how many X-intercepts? Well, there's one here for sure, and I guess like you can't quite tell for absolute certain. But let's zoom in real close. Does that look like it's actually making it to the x-axis itself? Yeah, so I would count that as an intercept as well. So it's got 2 intercepts. How many turning points? 2. It looks like it goes from increasing to decreasing back to increasing. So these all have like some different looking behaviors. But what I'm going to do is zoom out and try to convince you that while they look like they have different behaviors, on a really, really big scale, they look really similar. So here's the window I'm going to go for. Let's view this also from x equals 100 should be big enough, negative 100. I know it says 1,000 to negative 1,000, but 100 is big enough. Do those graphs now all look pretty similar? Yeah, so, and that's only from negative 100 to 100, not from negative 1,000 to 1,000. They all look basically the same, with the only difference being something about scale. And let's figure out the something about scale. So I'll leave the blue one. The blue one is x cubed. There's just x cubed. There's x times 2x squared plus 1. How does the green graph compare with the blue graph? Would you believe it if I said if you took any of the y coordinates on the blue graph and doubled them, you would get a y coordinate on the green graph? Yeah, and maybe we could eyeball that a little bit. Let's look at 50. Double that, you'll get, yeah, it's about double. It's not on the nose, but it's close enough. So to go from here to there, the y values double. Do those two graphs look pretty similar too? I guess like it looks even bigger than the green graph, taller than the green graph. And let's just see about what factor. So there's 1, 2, 2 are the first couple digits. 370, 366-ish. It's about tripling, it looks like. To go from here to there, y values triple. And now let's look at that last graph. Can you tell the difference between those two graphs? Not at this scale. So, I might jump to the bottom of the page now because we see something from that last example. Any of these degree 3 polynomials, they all basically look like the graph of x cubed, maybe with a multiple next to it. That's always true. The graph of a degree d polynomial, that degree d polynomial, zoomed out sufficiently far, looks like the graph of that constant multiple times x to that power. Oh, of course you can. All I did was write down the biggest term. The biggest term controls the asymptotic behavior of a polynomial. And now let's count up some other things. So this was just degree 3. A degree 3 polynomial, don't need that anymore. What's the greatest number of roots we saw on all of the degree 3 polynomials? 3. So in general, that's always true. Any degree d polynomial has at most d roots. So let's count up something real quick. So imagine in your head the graph of a degree 1 polynomial. So a line. How many turning points does that line have? None. A degree 2 polynomial, a quadratic function. So degree is 2. How many turning points are there? 1. Amongst all of those degree 3 polynomials, what's the greatest number of turning points you saw? 2. This pattern persists. Any degree d polynomial has at most d minus 1 turning points. Those facts seem believable enough from the example anyway? And maybe we'll test this. No, I think I won't test it. So let's go on to the next page where we will try to identify things about a polynomial from its graph. So let's suppose I told you that is a polynomial of some sort. Let's try to say what we can say about it. How many roots does it have? 1. So you know that its degree is at least 1? That's not so impressive though, is it? And in fact, its degree is obviously bigger than 1. How many turning points does that graph have? 2. So what can you tell me about the graph because of that? Could it be a degree 1 polynomial if it has 2 turning points? Could it be a degree 2 polynomial with 2 turning points? Could it be a degree 3 polynomial with 2 turning points? And anything bigger than that as far as we know. Let's try to measure its asymptotic behavior. So imagine these extended on forever. Don't do that to your notes. It'll make your notes unreadable, but I'm okay with it on mine because I have no eraser. So if you were to imagine zooming out of that graph so that you couldn't even see that behavior in there, what type of polynomial does it look like now? Even power function or odd power function? Odd power function. It's going from negative to positive. Even power functions do that. Does it look like a power function that's the right way up or that's been flipped over the y-axis? Does it look like x cubed or negative x cubed? X cubed. So it looks like x to the power odd. It's probably cubic, but it could be something to the 5th power. I can't tell. So what conclusion can you make? You know that this is odd degree at least 3 with positive leading coefficient. All that makes sense? So you can read off some things about what type of polynomial that might be just by looking at the graph. So let's go back to x times x minus 1 squared, which you can go back to the previous page to look at, but I guess I still have it pulled up right here. So its graph looks something like this. So it's got 2 roots, one at x equals 0, one at x equals 1. Oh, you couldn't see that, but you know what I wrote. Those two roots, they don't look, like they look different though, right? One of them is also a turning point, the other one goes straight through. So here's what I'm going to advocate. Let's zoom in real tight on those 2 roots using a computer. We'll describe what we see. So let's zoom in on this root at 0. Actually, this is the easiest way. What does that graph look like at a really small scale? Linear. In fact, it looks like y equals x. So near x equals 0, what graph do we see? We see that graph, something that's basically y equals x. You don't see what I drew. I need to get better about that. So it looks like y equals x. Let's do the same thing near x equals 1. So I'll go from x equals, there we go. There are enough zeros now. What would you say that graph looks like? Y equals x squared. It looks like it's pretty damn near on the nose. guess if we wanted to like really check that, let's add a graph. But I guess not really x squared. It's really more like x minus 1 squared, right? It's shifted. So there's that. Can you really tell the difference at all at the scale? Nope. So if there's the point 1, 0, this graph looks basically y equals x minus 1 squared, at least near x equals 1. And this is the type of, this is the segue into the third thing that I want to say in this particular notepad about behaviors of polynomials. You can read off behaviors near the roots by just studying what types of roots they have by the following rule. So, if a polynomial is factored, you can read off the graph. If you have a polynomial, p of x, and you have it factored as q of x times some number of x minus c's, then close to x equals c, you can find the graph. It will basically look like x minus c to the power of p, except with a coefficient next to it. P of x will be really, really close to x minus c to the power of p, but multiplied by a constant. So, thing's written down, but let me write down in words what this is saying. If p of x has a root at x equals c, then near x equals c, p of x looks like plug in x equals c to all of the stuff that's not equal to c, not equal to 0 at c, times x minus c to the power of p. How does that seem? Like, it seems like that's an abstract seeming statement. I think it will seem much more explicit if we use this for some examples. And maybe we'll even just see if it agrees with this. Let's see if this agrees with what we did above. So right here we see p of x equal to x times x minus 1 squared. So it has two roots, one at x equals 0, one at x equals 1. It's already factored. Which of the two factors gives you the 0 at x equals 0? The factor that's x. So that theorem said that near x equals 0, p of x should be somewhere around the thing that gave you the 0, x, times plug 0 in for all the other x's. Did that agree with what the graph we got says? Cool. Near x equals 1, well, which of the factors resulted in there being a 0 at x equals 1? The x minus 1 squared. So near x equals 1, p of x should be close to, plug in x equals 1 to all of the factors other than the x minus 1 squared, times x minus 1 squared. Oh, cool. Is that exactly what we got? Bangarang. So here's what I want to do next. I want to use this to do some graphing by hand, which we will then check via machine. If a polynomial is factored, you can read off its graph. So let's try to graph some polynomials. So I will first try to graph this polynomial. Y equals x times x plus 1 squared times x minus 2 cubed. So let's first find the zeros. So where is that equal to 0? What x values make that equal 0? Negative 1, 2, and 0. Does that agree? Anyone want that talked about? Okay. Right, it was just each of the factors. Let's draw those. X equals negative 1, x equals 0, x equals 2. I'm not going to worry a huge amount about having consistent scale. I just want vaguely the right structure. So let's check the behavior of this polynomial near each of those zeros. So close to x equals 0, I'll remember the factor that gave me the 0 at 0. So that's the x. So this polynomial is close to x times, plug in 0 for the rest of the x's, x plus 1 squared times 0 minus 2 cubed, and let's just expand that out. So that'll be x times 1 times negative 8. Oh, neat. We know what the graph of negative 8x looks like. It's linear. Slope is negative 8. And I'm not going to try to be fancy about having exactly the right scale, but that slope looks like it's around negative 8-ish. Do the same thing at the rest of the roots. Near x equals negative 1, y is about equal to, so I'll remember the factor that gave me the 0 at negative 1, so the x plus 1 squared, times plug in negative 1 for the rest of the x's. Negative 1 times negative 1 minus 2 cubed. So that's negative 1 times negative 3 cubed times x plus 1 squared. So that's x plus 1 squared times what? So, I'm going to ask you a question because I'm noticing something that I did that was wrong that nobody called me out on. What have I done that was wrong so far? Does that straight line look like it has negative slope? Does it look like it has positive slope? So it has negative slope there. Here, this is going to look like a parabola. Upward opening or downward opening? Upward, because 27 is positive. So if I were to say, draw this, would you stop me? Yes?
Yes.
Good. So notice, like, 27 is a pretty big number, so it's a fairly stretched vertically parabola. But at the scale I'm not going to try to have any reasonable scale. Close to x equals 2. Well, same thing. What is this pretty close to when x is close to 2? It's close to something times x minus 2 cubed. Right here in 18. Oh, but notice, so do you think that I actually care whether it's 18 or 180 or anything positive? All I really care is it's positive. But it's good to know it's 18 on the nose. So the graph will look something like that. It'll look like a cube function shifted and then stretched. And now let's interpolate between somehow. And now let's get asymptotic behavior. What's the degree of that polynomial? By that I mean the polynomial that we started with. So imagine you FOILed this all out. Don't actually do it, but imagine you did. What's the biggest power on x you would see at the end?
9.
I think 6. 6, right? So this will kick out an x cubed when you FOIL it out. This will kick out an x squared. X squared times x cubed is x to the 5th. Then you'll multiply it by another x, so x to the 6th. So for big x values, this base function is basically y equals x to the 6th. Oh, maybe we should also ask that. So imagine you did FOIL it out. What would the coefficient in front of x to the power 6 wind up being? So the only way you could get the x to the 6th is by using the x from both of those x plus 1. So there would be an x cubed term, but with 1 in front of it. You would have to use each of those x's, so they all have 1s in front of them too. So it is actually 1 times x to the 6th. Oh, but we know what the graph of x to the 6th looks like. So that tells us what the asymptotic behavior of this is, what the big x value behavior is. Let's just add that to the graph. Look like x to the 6th, and that's kind of like what the graph of x to the 6th looks like. Of course, I've caught back on myself, so I failed the vertical line test, but groovy. So with that done, let's see by looking at a machine if this graph is reasonable. It's not going to be good, but it might be reasonable. It captures some correct structure. X times x plus 1 squared times x minus 2 cubed. Click out of this, go to home. Does that look about like what we have? Yeah. I guess like it looks like those valleys are deeper and that peak is higher, but I didn't indicate where any of the hash marks were on my graph for a reason, because I wasn't going to try to get any of them right. So I guess there's one thing that we do see looking at this graph. Is there a local maximum somewhere between -1 and 1? Yeah, our graph can't tell us anything better than that. By looking at the actual computer-generated graph, I guess you could get that it's about there. Groovy. Any questions about this idea? So I'll give you one of two choices on this next example. We can talk through it together again. I can be quiet for a minute and let you all do it. So some people would like me to talk through one more example. All right, then I will do. If you don't want to listen, well, you have the things to do in front of you. If you would like to just do them. So let's go for it. So here is a polynomial. Maybe we'll ask this question first. What's the degree of that polynomial? Yeah. I think it's bigger than 4.
6. 7.
It's bigger than 6. I think it's 7. So this will kick out on x squared term. This will kick out, if we FOIL that out all the way, an x to the 4th and some other stuff. This would kick out well an x. So we have an x squared times an x to the 4th times x. I think the biggest term will be x to the 7th. In general, here's a fact. Degree adds under multiplication. If you have a degree 5 times a degree 7, the degree at the end will be 12. So the degree is 7. For big x values, this will basically be x to the 7th. So there's one thing that's easy to check. Let's check out the behavior close to each of the roots. So close to x equals 0, we should remember the term, the factor that gives us the 0 at 0. So which of the factors does that? Which of the factors do I need to remember? The x squared. So for x values really close to 0, y is about equal to x squared times, and now I'll plug in 0 for all the other x's. And as long as I don't actually care about what that multiple next to it is, I just care if it's positive or negative. Let's just ask if it's positive or negative. 0 minus 2 to the 4th. Without computing, it's positive or negative? Positive. Anything to the 4th power is positive. Even if you don't know that it's 16, you know it's positive. 0 plus 1, positive or negative? Positive times positive is positive. I guess we even know it's 16 at this point, but I don't care that it's 16. It's about a positive number times x squared. So close to x equals 0, this should look like an upward turned parabola. Near x equals negative 1, which of the factors gives me a 0 and x equals negative 1? X plus 1. So I'll remember this term, and I'll replace all the other x's with negative 1. Negative 1 squared times negative 1 minus 2 to the 4th times x plus 1. Is it a positive times x minus 1 or a negative times x minus 1? Gesundheit. Positive. A positive number times x minus 1. Yeah, of course it's x plus 1. Thank you. So that means here, close to negative 1, 0, I should see a straight line with positive slope. People with me so far? All right, now near x equals 2, I'll remember the term that gives me a 0 at negative 2. Positive 2. So it'll be an x minus 2 to the 4th. And I'll replace all the other x's with 2's. So 2 squared times 2 plus 1. So that's x minus 2 to the 4th times something positive or times something negative. Cool. So close to that point, I should see an upward pointing thing that looks like x to the power of 4. To 0. I tried to make that flatter than I usually draw my parabolas, but it's hard to tell. Now we'll interpolate between. And I know asymptotically it looks like x to the 7th. So if I want to ignore all that, what does x to the 7th look like? Something like that. How did that feel? Reasonable enough? Think we could check that using a computer? We have enough time to do so. Oh, so maybe I'll point out this. It looks like there are 2 humps. It looks like the second one is like stretched out but a little bit taller. Do you think that I should believe that? I have no reason to, right? I drew that by just doing something. A 50-50, it's right or wrong. X squared, x minus 2 to the 4th, times x plus 1. Does that qualitatively agree with what I got? Yeah. Was I right about which up was taller? No, but I had no reason to believe I was. This is the thing to remember about these graphing by hand techniques. You know exactly the things that you're careful to check. You can see some things in the consequence. The only way I can see the graph I got is if there are those turning points. There are those turning points. I couldn't tell how tall they were. All right, so at this point, I'm done. I'll see you all tomorrow. And hopefully, sometime I'll see what the issue is with that Friday the 18th or 20th.
grab the graph out.
Yeah, so basically you're just doing this stuff in your head, right?
Yeah.
If they were like clumps, like if it's like a whole, and they're like this exact clump, I want you to answer that clump, then you better answer it. But yeah, if I just ask you, sketch a graph of this qualitatively, and you can describe in log, like, oh, I see a parallel ball on the x minus 2, so I should be 100 by x to the box. I got it. Then yeah, that's awesome.
I take the quiz on Friday as a class.
You get quiz on Friday. Yeah. Send me an email letting me know exactly when you would like to take the quiz on Friday.
I can do it after class.
Okay, send me the email anyway. And then what I'll have you do is if you go to the elevator, I'll take you to the 5th floor, and Tom left, there'll be a place called Mac Apartment Office. Yeah.
I was asking the same thing, so I sent an email before and I missed Monday. Do you know if days or times would work for making that up?
I can schedule you to take it during any reasonable business hour. I just won't be the one to talk about it.
Alright.
So send me an email. I'll have you take it through the Math Department office, which is on the 5th floor. And I'll try to give specific instructions when he says Monday from the scheduling meeting. Before you leave, you have a question? Okay.
Hi. So I sent an email asking if I could take it either Monday or Friday. So that he's wondering which day.
Do you know what time is it?
Okay. And then.
Do I know how Friday yet?
No, not yet.
Okay. When did you send it?
Monday.
Monday. Okay, so I missed it. Okay.
Alright.
Yeah, I'll go back and check that.
Okay. And then I heard that you can do revisions for open-ended for February. Is that correct?
That sounds right. That's the one where it's like, here are some points.
Yeah.
Yeah.
Okay, perfect.
Yeah. It'll be, so it depends on what score you got. I think I said allow revisions up to 60% or something.
Okay.
It's because a lot of people kind of missed the point of the problem and they wound up getting 40%. Okay, so if you're on that one, then yeah.
Okay, thank you.
Yeah. So the extra credit, there's this in a few hours. The deadline for doing it is when I go home on the last day of the semester before our final week. And what you'll do is you'll have that walkout. You'll come into my office and you'll present it. So you'll talk me through it and I'll ask you some questions.
Okay.
Yeah. You're going to do it?
Yeah.
Did I hit stop recording? Nope. So all of that was recorded.